Welcome to Tomorrow Unveiled, the program dedicated to sifting through the noise of innovation and pinpointing the critical shifts that are, really defining our future.
And what a week to be doing it.
Absolutely. We are just coming off what our dedicated research team unanimously called, and I think this is a direct quote, the definitive inflection point for robotics.
It really felt that way. All the announcements, especially around the close of the 2026 industry cycle, it just felt different this time.
How so? I mean, we've seen cool robots for years.
We have, but they were always discussed with qualifiers. They were promising prototypes or fascinating lab experiments.
Or my favorite, the viral backflipping machines of YouTube.
Exactly. Fun to watch, but not exactly practical.
Yeah.
But based on this huge stack of sources our research team compiled this past week, that all changed. Robots stopped being research projects. They've officially transitioned into, well, industrialized, scaled, and standardized products.
And that transformation, the incredible leap from a science curiosity to an actual industrial commodity, that's our core mission for you, the listener, today. We need to unpack the consensus that really emerged from this flood of information.
Right.
Our goal here is to clearly identify the critical technological shifts that are actually happening right now. First, the industrialization of humanoids, really mass production.
And second, the rise of the specialized AI brain that defines their intelligence. That's a huge piece of the puzzle.
And finally, the new frontier, the new challenge, which is robotic dexterity, basically solving the problem of the hand.
And, the single overarching theme that just ties all this kinetic energy together is the definitive rise of physical AI. That's the core concept.
Okay, so break that down. Physical AI, what does that mean in simple terms?
It means we're moving beyond pure automation. A robot on an assembly line that just welds the same spot on a car door over and over. That's a dumb machine following a rigid, pre-programmed path.
Right.
Physical AI means the machines are capable of context-aware reasoning. They can see a cluttered workshop, understand what's in it, and plan a path through it. They have real-time adaptation and, critically, safe and reliable interaction in these complex, messy human environments.
I think for me, the most staggering finding from the research team wasn't a specific robot or a new piece of software. It was the sheer industrial commitment, the money.
I agree completely. It's the metric of scale that proves the shift is real. You can promise anything in a press release, but capital expenditure doesn't lie.
We're talking about industry leaders, not just, raising some venture capital, but actively building multi-hundred-million-dollar factories. Factories capable of producing, what was the number?
Tens of thousands of complex humanoid robots.
Annually.
Annually. That's a number that's hard to get your head around. This isn't research funding anymore. No, this is strategic capital expenditure. They're preparing for a massive global industrial rollout. So the era of the general-purpose robot, it isn't some future promise anymore. It's a production line reality. The industry has stopped asking if humanoids are coming.
And now they're just asking how fast they can build them.
Exactly.
Okay, so let's start with the undisputed centerpiece of the week. I think, arguably the most recognizable robot on the planet.
Have to be Atlas.
It has to be Atlas, specifically the transition of Boston Dynamics Atlas. For years, this thing was the hydraulic superstar.
The Acrobat.
The Acrobat. The machine that showed us the absolute limit of what dynamic mobility could look like. The running, the jumping, the parkour.
And, of course, the legendary backflips.
But the source material confirms this enormous pivot, a pivot to the electric Atlas.
It's a move from, frankly, an expensive, fragile, and incredibly noisy viral sensation to a reliable, maintainable enterprise asset.
So the old Atlas, the one we all know from the videos, it was all driven by high-pressure hydraulic fluid systems.
That's right. Which, from a technical standpoint, was a marvel, an absolute marvel of engineering.
But not practical.
Not even remotely practical for a real-world factory. Hydraulics require immense power, they generate a ton of heat, a ton of noise, and they're prone to all the maintenance issues you'd expect from fluid-based systems. Leaks, contamination. It's a non-starter for a clean, reliable factory floor.
So what does the electric Atlas gain in this trade-off?
It gains everything necessary for industrial acceptance. The new version is confirmed to be fully electric. That means it prioritizes safety, it's nearly silent in operation, and most importantly, it's predictable and reliable.
And in a factory setting, unpredictability is the enemy.
It's the enemy. Unpredictability means failure, and failure means massive cost. So this electric platform, it fundamentally solves that maintenance headache, and it ensures the machine can operate safely near humans without, the risk of high-pressure fluid leaks or excessive heat.
And the physical specs on this production model they're really surprising. I mean, I was shocked by the numbers our research team presented. It features 56 degrees of freedom.
56?
That sounds almost excessive. I mean, compared to a human body.
It is excessive, and that's by design. A human has, what, around 25 to 30 controllable degrees of freedom in functional movement?
So why double that?
Because it's maximizing utility,
Yeah.
not trying to perfectly replicate biology. The key is that those joints are predominantly capable of 360-degree rotation.
Which a human elbow or knee definitely cannot do.
Exactly. And that allows for these highly optimized, almost alien-like movements in complex industrial spaces. Imagine it twisting its torso completely around to grab a part behind it without moving its feet.
Or reaching into some confined gap in a piece of machinery that a human operator just couldn't physically contort themselves into.
That's precisely the idea. It's about superhuman range of motion, not just human-like movement.
And this machine isn't delicate either. The source material makes it clear this is built for brute industrial strength.
Absolutely. The Atlas is designed to handle serious payloads. It's rated for lifting more than 70 pounds. That's about 32 kilograms.
Which is more than enough for most common factory parts, specialized tools, logistics packages.
It's the sweet spot for a huge range of industrial tasks. So this is not a lab experiment anymore. It's a serious, rugged piece of industrial machinery designed for high-throughput endurance.
But the hardware, as impressive as it is really only half the story. The research highlighted that Boston Dynamics and their parent company, Hyundai Motor Group, are moving at, well, breakneck speed.
The speed is incredible. Production has already started, and crucially, the entire 2026 supply is already allocated.
So you can't even buy one if you wanted to.
Not this year. It's all going straight into Hyundai's own operations and to a few select AI research partners.
But it's the headline number that truly validates this whole industrial thesis for me. The confirmation that a new factory is planned.
A factory capable of producing an estimated 30,000 Atlas robots a year.
30,000 a year.
That kind of commitment, it's not just a sign of confidence. That's a complete re-rating of the entire industry.
It is. It means they anticipate a clear, immediate, and massive demand that warrants that level of initial capital investment.
This just sets a new precedent for mass manufacturing in the entire sector.
It really does. I mean, we need to remember that the manufacturing of humanoids has traditionally been, bespoke. It was low volume, almost artisanal work.
And now they're talking about scaling into the tens of thousands almost overnight.
It's a paradigm shift.
So where are these 30,000 machines going first?
Yeah.
Because the deployment roadmap is really strategic. It's not, straight to consumer homes, which I think surprises a lot of people.
Oh, definitely not. People see a bipedal robot and they immediately assume it's coming for their dishes.
Right. But that's not the plan. No, the initial rollout, which is slated to begin by 2028, is targeted for Hyundai's massive new manufacturing facility in Georgia, the Robotics Metaplant Application Center, or RMEC.
And they're starting with the most strategically sound tasks, the low-hanging fruit.
The famous dirty, dull, and dangerous jobs.
Of course.
Exactly. They'll be handling low-risk, repetitive tasks first. Things like parts sequencing, making sure the right components arrive at the right assembly station in the right order, and basic material handling.
It's a phased approach, which is critical.
So critical. You start where the return on investment is clearest, where the complexity of the task is manageable, and where the robot can build up a reliable performance track record in a controlled environment.
And the plan is to scale up from there.
Yes, up to more complex assembly work by 2030, which requires the Atlas to not just move like an athlete, but to think like a worker.
So we've got this durable, strong electric body, but that hardware needed a brain transplant.
A serious one.
And this leads us directly to the strategic AI integration with Google DeepMind.
It had to happen. The complexity of modern factory work means the intelligence gap is now the biggest challenge. Boston Dynamics, they mastered what you might call athletic intelligence.
The balance, the dynamic recovery from a push, the sheer locomotion.
All of that. But that is fundamentally distinct from the cognitive intelligence required for a generalized factory worker. A worker who needs to understand novel instructions, adapt to clutter on the floor, and prioritize tasks on the fly.
And that's where the sources really emphasize this collaboration. The integration of Google's Gemini Robotics foundation models directly into the Atlas platform.
It's the perfect synthesis. You have the world's most capable humanoid hardware fused with one of the world's most advanced reasoning engines.
This is what allows the robot to move beyond just following a pre-programmed path.
To genuine task understanding. And crucially, the sources highlighted their emphasis on what they call teacher-student learning.
Okay, what is that?
It means that instead of engineers writing millions of lines of code for every possible scenario, human operators teach the robot. They use demonstrations and real-world teleoperation. The data from those sessions is used to continuously refine the AI's understanding.
So you instruct the robot by example, you show it how to do a task.
You show it. You don't program its every single move. It learns from you.
But if the end goal is hyper-efficiency and mass production, doesn't that make the logical endpoint full replacement of human workers? Yet the core philosophy that kept popping up in our sources was this term, human-centered robotics.
Right.
So are they really building collaborators, or is that just, good PR?
I think it's both, but it's primarily a pragmatic reality, at least for the initial industrial deployment. The goal right now is collaboration and augmentation. Because in a massive, complex factory like RMAC, the most viable path to adoption is to ensure these machines work alongside people. They enhance human capability. They handle the heavy lifting, the repetitive strain tasks. Plus, you need human oversight for safety and human input for novel, unexpected problems.
So the message is clear. The focus on verifiable safety and collaborative augmentation is essential. It's about building regulatory trust and industrial buy-in.
Absolutely. It's a necessary first step before any company dares to even talk about full replacement. They have to prove, beyond a shadow of a doubt, that these machines can operate safely in shared workspaces.
So we've established the body, the incredibly capable Atlas hardware, but now we have to turn to the brain. The consensus across the entire industry, from every source our team looked at, is that the true bottleneck for general-purpose robotics is no longer the mechanics.
No, the body is, for the most part, a solved problem.
The bottleneck is now agentic reasoning.
Agentic reasoning. It's the ability to process complex, multimodal data vision, touch, sound, and plan multi-step actions in real time, all under conditions of uncertainty.
And this is where the infrastructure wars are really being fought.
Absolutely. Our research team noted that NVIDIA is positioning itself to be the standardized infrastructure provider, what some sources are calling the Android for generalist robots.
So the idea is, if you're a company building a robot, any robot,
if you intend to deploy physical AI that can actually reason and interact with the world, you will almost certainly be doing it on their software and hardware stack.
Okay, so let's unpack their pivotal software suite. It all starts with something called Project GR00T. That's GR000T.
GR00T, which stands for Generalist Robot 00 Technology.
Pitchy.
Very. The latest version, N1.6, is the foundation model. It's purpose-built from the ground up to understand humanoid physics and movement.
So think of it as the robot's core motor cortex and its language processing center all rolled into one.
That's a great way to put it. It's designed to learn from human demonstrations and also from simulation. It integrates locomotion, the walking and balancing, with dexterous manipulation, the hand and finger movements.
Which used to be two completely separate, incredibly difficult control problems.
Two different fields of research almost. And GR00T N1.6 successfully achieves what they call whole body control. The brain is directing every joint in concert to achieve a goal.
But a foundation model, just like a human brain, it needs a world to learn in. And that leads us to the Cosmos ecosystem. This is what tackles the massive data scarcity problem in robotics.
The 100,000-year data gap, as it's sometimes called.
Why is data so much harder to get for a robot than for, say, a large language model like ChatGPT?
Because a language model only needs text. There's an almost infinite amount of it on the internet. A robot, on the other hand, needs millions of hours of physical, real-world trial-and-error interaction data to learn how to, say, open a door.
And getting that data is prohibitively expensive and incredibly slow.
Exactly. You can't just have 1,000 prototype robots running around for a century to collect data. So the Cosmos ecosystem addresses this by training robots in high-fidelity simulations, basically AI training environments that strictly obey the laws of physics.
So you can think of the Cosmos suite as this sophisticated digital nervous system that powers the robot's intelligence.
Right, and it's broken into three key cognitive components.
Okay, first up, we have Cosmos Reason 2. What's its function in this nervous system analogy?
Reason 2 is the robot's high-level cognitive function. It's the executive planner. It's a reasoning vision language model, or VLM, that allows the robot to understand semantic context.
So it doesn't just see a red plate on a table?
No, it can distinguish between a clean plate and a dirty plate. It can understand an instruction like put the heavy box on the strong shelf, not the flimsy one. This kind of high-level planning and action sequencing is what moves a robot from being a specialist tool to a true generalist specialist.
Then there's Cosmos Predict 2.5. This sounds like, I don't know, the AI version of foresight or imagination.
That is exactly the right analogy. Predict 2.5 is a world generation model that simulates potential future states. It gives the robot the crucial ability to imagine the consequences of its actions before it executes them.
Which is absolutely safety critical.
Oh, it's everything for safety, especially for a heavy industrial robot like Atlas. A simple rule-based system might not understand that dropping a 50-kilogram gear from a height will crack a concrete floor.
Or worse, hurt a nearby human.
Exactly. But Predict 2.5 allows the agent to simulate that consequence in a split second and decide to adjust its grip or change its trajectory or just slow down. It's the difference between reactive safety stopping when you hit something and proactive prudence.
And finally, the third piece, Cosmos Transfer 2.5. This is the engine that makes this whole simulation-first idea economically feasible, right?
It's the great data compressor. Transfer 2.5 is the tool that generates physically accurate synthetic data. By running training in these virtual environments, they're often called Isaac Labs or GEMs, that are physically indistinguishable from reality.
In terms of friction, gravity, material properties, all of that.
All of it. Developers can compress millions of hours of real-world trial and error training into just a few days. This synthetic data generation is now the consensus standard for quickly training complex industrial agents for firms like Boston Dynamics.
So we have the foundational models and the simulated training world, but all this complex reasoning needs specialized hardware to run on. And our research team highlighted a massive shift away from general-purpose chips like NVIDIA's Blackwell.
A huge shift.
Yeah.
Towards the new silicon, the Vera-Rubin architecture.
This is a crucial distinction. It really clarifies the path forward for physical AI.
It does, because a chip like Blackwell was optimized for training these huge generative models. Think of it as the hardware you use to write the great American novel.
Okay.
Vera-Rubin, in contrast, is optimized specifically for agentic workloads. That means inference and execution. In our analogy, it's the hardware for performing the actions described in the novel in real time in the real world.
So why does running the brain require different hardware than training the brain?
Latency. Latency is a catastrophic failure condition in robotics.
A delay of even a fraction of a second could be disastrous.
Could be the difference between success and failure. When a robot is executing a task, especially one involving balance or heavy lifting, it needs guaranteed real-time reactions. If an Atlas is balancing that 50-kilo load, it cannot afford a microsecond pause while its processor waits for a thread to unblock.
So how does Vera-Rubin solve that?
The key feature is something called spatial multithreading on the Vera CPU. It offers 176 total threads.
And that architecture specifically addresses that low latency necessity.
It ensures deterministic performance. It guarantees that the critical control loops, the constant calculations required for balance, motor feedback, and safety are always prioritized and executed with extremely low latency.
Even while the high-level AI reasoning is happening in the background.
Exactly. It means the robot's reaction time is reliable and instantaneous. Without that deterministic performance, the safety certification required for industrial use would be impossible to get.
And then there's the economic implication of this new architecture, which is really what's going to drive mass adoption in logistics and retail.
Absolutely. This is the financial tipping point.
Yeah.
The source material shows that this new architecture reduces the cost of inference. That's the cost of running that intelligent brain in real time by a staggering 90%.
90%.
A 90% reduction. What used to be a prohibitively expensive capital expenditure for high-value manufacturing is now becoming economically feasible for nearly every application. Warehouses, retail stores, eventually even our homes. The brain is getting cheaper, faster, and safer all at once.
Okay, so we've covered the body, the electric atlas, and the brain, which is NVIDIA's physical AI stack. Now we have to talk about the work itself, which means manipulation, the hand.
The final frontier.
It really is. The consensus from all the industry presentations our team analyzed was crystal clear. Mobility walking, dynamic balancing, that is largely a solved problem now.
For the most part, yes.
But dexterity, the ability to manipulate the world effectively with hands and fingers, remains the primary barrier to unlock the true economic value of a generalist robot.
You said it perfectly. A machine that can walk anywhere but can't open a door or can't handle a small screw with any precision is, at the end of the day, functionally useless.
This is what our research team called the last millimeter challenge. I love that phrase. It really encapsulates the problem.
It's a brilliant way to put it.
Yeah.
Because conventional vision language action models, the VLAs, they're fantastic at generating the initial coarse movement. They can get the robot hand close to the object.
Right, they can get it in the ballpark.
Exactly. But they fail at the precise, real-time adjustments required during contact, that crucial final millimeter.
It's like reaching for a light switch in a pitch-black room. You can get your hand close based on your memory of the room's layout.
But you need your sense of touch to actually find and flip the switch.
Right.
These older models, they lack the high-frequency force and tactile-based feedback loops that are necessary to prevent dropping the object or crushing the object or just failing the insertion task completely. The physical world is messy and unpredictable.
So how are developers solving this tactile blindness? Our research team highlighted an architecture called CraftNet. It's a hierarchical system designed to mimic human cognition.
It's a really elegant design. It splits the decision-making process into 3 asynchronous systems, which decouples the slow, high-level planning from the instantaneous physical reaction. It's a lot like our own central and peripheral nervous systems.
So at the top you have System 2, the reasoning brain.
Right, and it operates slowly, around 1 hertz or 1 cycle per second. This is the VLM, the big language model, handling the high-level semantic understanding, the long horizon intent.
So it gets an instruction like make dinner or clean the workbench.
Exactly, a broad conceptual goal.
Then you have the intermediate layer, System 1, the motion brain, which steps up the pace to around 10 hertz.
System 1 is the core motion planner. It takes that high-level instruction from System 2 and translates it into a detailed but still coarse motion plan. It figures out the joint trajectories, the optimal speed, the pathing to avoid obstacles. It's responsible for getting the robot hand to the vicinity of the object efficiently.
But the real quantum leap here is System 0, the interaction brain. And this is where the last millimeter is won or lost. It operates at a blistering 100 hertz.
Around 100 hertz, yes. System 0 is the super high-frequency model that leverages real-time tactile feedback, the robot's sense of touch, to continuously adjust the hand and finger positions during contact.
So if the robot grabs a fragile wine glass...
System 0 is making microscopic force adjustments dozens of times per second based on the pressure it's feeling, any slip detection from the sensors, the material's compliance. This high-frequency, low-latency loop is what enables the kind of fine motor control that previous unified VLA models just couldn't achieve because of their inference latency.
To make this abstract technology a bit more concrete, our sources pointed to some specific demonstrations of extreme dexterity from a company called Sharpa Robotics and their North Humanoid.
Sharpa's work was stunning. They showcased their 22 DOF Sharpa wave end effectors, the hands, which are themselves a massive hardware breakthrough.
How so?
They feature over 1,000 tactile sensors per fingertip.
1,000.
1,000.
Yeah.
That incredible density of sensing is what feeds the data into that 100 hertz System 0 loop. And the capabilities they demonstrated were just mind-blowing.
They showed the North robot successfully rallying in a game of ping pong against a human opponent.
It's a spectacular technical feat. I mean, a robot playing ping pong is one thing.
But winning a rally, that requires a reaction time faster than human neural transmission speed. It's both terrifying and amazing at the same time.
It is. To successfully return a ping pong ball in a rally requires a visual motor reaction time of approximately 0.02 seconds. The latency between the visual system seeing the ball's trajectory and the motor command being sent to the paddle has to be that fast.
So this is real-world validation that the low-latency CraftNet AI loop is operational and can handle instantaneous physical interaction.
It's the ultimate proof of concept. And beyond just speed, they prove the precision through incredibly delicate tasks.
Right, they had to autonomously assemble a paper windmill.
And even trickier, dealing cards from a deck.
Which proves the ability to handle delicate, deformable materials without crushing them. If you've ever seen an older robot try to pick up a single sheet of paper, you know how incredibly hard that is.
It's the ultimate validation of the CraftNet philosophy. Take a high-level instruction and execute a fine-grained action with continuous real-time force modulation. Every single one of these successful manipulation tasks, according to the CraftNet researchers, is a deposit into the human time bank.
The human time bank. I like that.
That's their core goal. They're not just manufacturing robots, they're manufacturing time for human operators.
As this advanced robotics technology matures, we inevitably start to see strategic consolidation. and this week delivered a major one that bridges autonomous driving and physical AI.
It was a big one. Mobileye's agreement to acquire Minty Robotics for approximately $900 million.
A huge deal.
Huge. And Mobileye CEO, Professor Amnon Shashua, he called this the launch of Mobileye 3.0. It's highly significant because it strategically merges two fields that, at first glance, they seem distinct.
Automotive safety and generalized humanoid robotics.
But they share a massive technical overlap, a shared foundation.
And that shared foundation is the same, the need to operate reliably in a world that was built for humans.
Exactly. An autonomous vehicle and a humanoid robot both require the same fundamental stack. They need multimodal perception, LiDAR, vision, radar. They need world modeling to understand dynamic environments. And they need real-time decision-making under uncertainty.
So Minty brings a robust humanoid platform built on that simulation-first training principle we just talked about.
They do. But Mobileye brings the critical component for scaling into a regulated, public-facing industry.
Yeah.
Safety leadership.
And that safety framework is their Responsibility-Sensitive Safety Model, or RSS, which was originally developed to govern the driving policy of their autonomous vehicles.
That's right.
So how does that transfer to a robot walking around a factory or eventually a home?
That is the key intellectual property transfer in this whole deal. RSS isn't just simple collision avoidance. It's a mathematically grounded, verifiable foundation for defining and enforcing safe behavior.
What does that mean, verifiable?
It means it ensures the robot always knows its safe state. It will not enter a situation where, regardless of what another agent does, a human, a forklift, another robot, it can still avoid causing an accident. This verifiable safety framework is absolutely crucial for building the regulatory readiness and the public trust required for humanoids to become economically viable at scale.
So Mobileye is essentially giving the humanoid a verifiable safety certificate, which is what you'd need for insurance for regulatory approval.
Precisely. Minty is aiming for industrial deployments by 2028, and they're going to leverage Mobileye's established manufacturing scale and safety expertise to expand into the home market by 2030. They are betting that safety certification will be their key competitive differentiator, at least in the West.
Now, this global race for physical AI dominance, it leads us directly to the critical economic factor here, which is price disruption. While Atlas and Mobileye Minty are focusing on the premium industrial and safety segment, Chinese manufacturers are aggressively commoditizing the hardware.
This is the competitive dynamic that is just forcing down the cost structure across the entire sector. Our research team noted that Unitree Robotics, sometimes they're called the Boston Dynamics of China, showcased their G1 humanoid.
And this is clearly positioned as the Model T of humanoids.
Absolutely. It's designed to disrupt the market with an approximate price of just $16,000.
$16,000 for a high-agility humanoid. That just completely undercuts the projected costs of every single Western competitor we've discussed by an order of magnitude.
And its demonstrations showed it has competitive agility. It was doing high-speed martial arts, complex choreography like moonwalking. It validated its dynamic balance capabilities.
So what's the trade-off?
The trade-off, at least for now, is often in the proprietary software ecosystems and the long-term industrial endurance and verifiable safety required by Western standards.
Then there's another player, Engine AI, entering the heavy-duty industrial segment with their T800, which is priced around $25,000.
While it's a bit more expensive than the G1, the T800 is built specifically for raw industrial power and endurance. It delivers extremely high torque, 450 Newton-meters peak, which is suitable for heavy lifting in construction or logistics.
But its critical breakthrough, which the research team highlighted, wasn't the strength, but a sophisticated active cooling system integrated into the leg joints.
And that sounds like a minor detail, but it's monumental.
Why is active cooling so important for an industrial robot?
Because electric humanoids, especially ones carrying heavy loads or moving rapidly, they generate an immense amount of heat in their motors and joints. This leads to something called thermal throttling.
The robot has to slow down to prevent overheating?
Exactly, which kills productivity. The T800 solves this, allowing for 4 to 5 hours of continuous high-load activity on a single charge. That continuous operation time is comparable to the high-end Atlas model, and it's necessary to integrate smoothly into human work shifts.
So the performance gap is narrowing rapidly, but the price gap remains a monumental advantage for these Eastern firms.
Especially in markets focused primarily on the initial cost.
This cost disruption leads directly to the question of geopolitical fragmentation. or what some are calling the splinter net of robotics. Are we seeing two fundamentally incompatible technology paths emerge here?
Absolutely. The market is fundamentally splitting based on core competencies and regulatory concerns. The U.S. advantage is clearly in the software, the large foundation models from NVIDIA and DeepMind, the specialized chips built for inference.
And the China advantage is in hardware scaling, supply chain integration, and aggressive pricing.
Right. And the regulatory landscape, which is amplified by concerns over data sovereignty and security, means Western markets are likely to gravitate toward Western-brained robots. They need those verifiable safety frameworks like RSS, and they have strict data regulations.
While the rest of the world, perhaps the global south, opts for the more affordable Chinese alternatives.
Precisely. This competition isn't just about technical performance anymore. It's about control over the underlying AI ecosystem. If your robot's brain is trained on data governed by one state and your regulatory environment is governed by another, you're going to have friction. We are likely heading toward two dominant and potentially incompatible technology stacks dictated by geopolitical and economic priorities.
If you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future.
So while the humanoids commanded all the headlines, it's just so critical to remember that specialized robots are delivering immediate, measurable, and often life-saving value right now.
And nowhere is that clearer than in the medical field.
Absolutely not.
Let's start with surgical robotics, where the pursuit of precision and safety is just relentless. Johnson & Johnson submitted its OTT system to the FDA for de novo classification.
Which is a massive regulatory vote of confidence in J&J's new platform. The OTTAV system is designed as a multi-specialty soft tissue surgery robot.
Meaning it's engineered to handle a broad range of procedures, not just one thing.
A very broad range across different patient anatomies. It can even handle highly complex multi-quadrant surgeries. J&J is leveraging its decades of surgical expertise to build a platform that aims for universality in the operating room.
But the real breakthrough, the one that deals with feeling and patient safety, came from the upgrade to the venerable Da Vinci 5 surgical system.
Yes.
It finally introduced force feedback technology.
This is a true game changer for the surgeon. Historically, one of the greatest limitations of robotic surgery was the complete lack of haptic feedback. Surgeons could see, but they couldn't feel the tissue they were working with.
And now, the Da Vinci 5's force feedback allows surgeons to literally feel tissue tension through the robot's control.
It's like their sense of touch is being transmitted through the machine, and that's crucial for reducing trauma and preventing accidental tearing.
The data supports the impact, too. Our research shows this technology can reduce the force applied to patient tissue by up to 43%.
43%. That is a direct reduction in tissue trauma. It leads to better outcomes, faster recovery times, and it verifies the safety profile of the platform in a completely new way. It moves robotic surgery from purely visual precision to a combination of visual and tactile precision.
And then, addressing global access gaps, SS Innovations announced a critical development for their SI Mantra system. Their focus is on increasing accessibility to robotic surgery worldwide.
Yes, and they did something very important. They completed development of new 5mm instruments.
Why is that so significant?
Because most robotic surgery equipment has historically been geared toward adult anatomy. These much smaller instruments are specifically designed for pediatric and cardiac procedures. This development directly addresses the shocking statistic that 1.7 billion children globally lack access to critical surgical care.
So these 5mm instruments make robotic-assisted surgery feasible for infants and in much smaller anatomical structures.
It's a massive impact on a huge global health crisis.
Yeah.
All by increasing the affordability and accessibility of these precision procedures.
Okay, shifting gears completely now, let's look at the domestic front. The dream of the zero-labor home, LG debuted its Keloid robot. Pitched as a wheeled smart home hub powered by, and I quote, affectionate intelligence.
LG's Keloid really represents the grand vision of the generalist home companion. It's focused entirely on ecosystem integration. It talks to your ThinQ smart appliances. It coordinates your chores. It does personalized meal planning. It can even do wellness monitoring. It's the full vision of a friendly, helpful home AI.
But this is where our research team provided the very candid reality check. The vision is grand, but the execution, well, it exposes the practicality gap.
It does. While the Keloid can do the task, the efficiency just isn't there yet. Our sources noted that in the live demos, this only took nearly 2 minutes to fold a single piece of laundry.
2 minutes for one t-shirt.
And while that proves that technology makes the task possible, it knows what laundry is, it knows how to grasp it, it is currently very far from being practical or efficient enough to meaningfully replace human labor.
Or to justify its price point, I imagine.
Not yet. This really confirms that dexterity, especially with soft, deformable materials like cloth, remains one of the hardest problems in all of robotics.
So, if the full humanoid housekeeper isn't quite ready for prime time, where are the true domestic breakthroughs happening?
In specialized, focused utility robotics, where one specific high-value problem is solved elegantly,
And a great example is Robotic. They introduced the Saros rover,
which features a novel wheel-leg architecture.
which fundamentally solves the universal pain point of every robot vacuum ever made, stairs.
Exactly. This combination of wheels and retractable legs makes it the world's first robot vacuum that can autonomously climb stairs and transition seamlessly between floors of a house. That is immediate, measurable value for millions of people in multi-story homes. It solves a core limitation of the entire product category.
And the rover uses advanced AI to recognize over 200 types of household objects so it can avoid stray socks, pet messes, power cords.
All the things that stop a traditional vacuum dead in its tracks. That combination of breakthrough mobility, the ability to move through a multi-level human environment, and advanced spatial intelligence built on LiDAR and 3D sensors. It's just a perfect example of focused innovation. We also saw it in outdoor autonomy.
Like the autonomous lawnmowers.
Exactly, like the Rockmo X1. It uses RTK GPS and Vision LiDAR fusion to navigate complex backyards without needing those annoying perimeter wires you have to bury. The message is clear. Focused automation, where robots are designed to solve one problem perfectly, is winning the near-term domestic battle.
This week in robotics, especially coming out of CES 2026, delivered a fundamental, verifiable shift. It moves us out of the laboratory and onto the factory floor. So let's synthesize the 3 key takeaways for you, the listener, and summarize what this explosion of innovation means for Tomorrow Unveiled.
The first major takeaway has to be the official move from a fragile prototype to an industrialized product. The Atlas announcement, backed by that commitment to a 30,000 unit per year factory and a focus on safety frameworks like RSS, it confirms that humanoids are now enterprise assets.
Focused on verifiable safety, reliability, and collaboration within structured environments, they are finally ready for complex assembly work.
The second point is that the true value of robotics is migrating definitively from the hardware to the software. We are now living in the age of the software-defined robot.
NVIDIA's dominance with the GR00 and Cosmos Foundation models, coupled with the Vera Rubin architecture's 90% inference cost reduction, it means the machine's intelligence, its capacity for agentic reasoning, that's the premium product.
And the body itself is rapidly becoming a commodity.
And finally, that intensely competitive environment is leading to a major geopolitical split. Chinese manufacturing is rapidly commoditizing the hardware, which we see with that affordable, agile $16,000 Unitree G1.
While Western firms retain the lead in the proprietary AI ecosystems, the security frameworks like RSS, and the specialized chips. This means we are likely heading toward a fragmented global market. It'll be dictated by either superior, safety-certified Western AI or affordable, mass-produced Eastern hardware.
We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the future of humanoid robotics. Are you ready for a $16,000 robot assistant in your factory? Or maybe even your home?
And if you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners and keeps our mission viable.
So we discussed earlier how the CraftNet Architecture researchers view every manual task that's delegated to a robot as a deposit into the human time bank.
Right.
The economic consensus is that these safety-certified, highly complex, generalist specialist agents will handle the dirty, dull, and dangerous jobs.
Which raises the final provocative thought for the week. If this robot economy is successfully designed to augment human work, and the primary output we are manufacturing is not physical goods or services, but time freedom from mundane labor, what tasks will you, the human operator, choose to focus on when you regain that time?
And how will we measure the success of an economy whose most valuable product is freedom from labor? What new definition of human purpose will emerge from that?
A big question to ponder.
Food for thought for your week ahead. Thank you for joining us for this extensive dive into the rise of the machines, and we'll catch you next time on Tomorrow Unveiled.